Propulsion Lab. To her right is Michele Dougherty from Imperial College London in UK. To her right is Mark Perry from Johns Hopkins University Applied Physics Lab, and to his right is Matt Tiscareno from SETI Institute. So the speakers will speak in this order, and we'll take questions afterwards. But let me remind you to turn off your cell phones, or at least put them on silent before we begin. And we'll have viewers from the webcast asking questions as well. All right, Linda, take it on.
Thank you. Let's see, how do I get up the first slide?
Uh-oh.
Yes, I did.
Okay, good. Takes sense.
Okay, after 13 incredible years in orbit, the Cassini mission plunged into Saturn and vaporized just a month ago on September 15th. Yesterday was Cassini's 20th launch anniversary, and I vividly remember that day. I was there with my daughters and my husband for the pre-dawn launch as Cassini lifted off the launch pad and began this incredible journey. And I was also there with my Cassini family, and we have witnessed together many milestones of the Cassini mission, including the final plunge. Well, we've been analyzing the grand finale data, and there are lots of surprises. Saturn, its rings, and the region in between are not what we expected. And so today, we're going to discuss some of the findings from the new results from Cassini. Michele will be talking about the magnetic field of Saturn and a status report on where we are with those data. Mark Perry will be discussing the ion and neutral mass spectrometer data of Saturn's atmosphere, and Matt Tiscareno will be covering some of the results from the images of the rings. These are the 22 grand finale orbits. Each orbit was 6.5 days in length, plunging in between the gap between the rings and the planet. Gentle nudges from Titan allowed us to sample across that entire gap, including dipping our toe in the atmosphere of Saturn in the final 5 orbits. And you can see there's the final plunge into Saturn, ending those orbits. We had a variety of science, but mostly focusing on the planet itself, looking at Saturn from the inside out, as well as spectacular images and spectra of the rings and the planet itself. Here's a far ultraviolet view of Saturn's Aurora. It was taken on the day before the plunge. We got some of our highest resolution data. This is of the North Pole of Saturn, as the energetic particles are crashing down into Saturn's atmosphere. The aurora on Saturn are pink at the bottom, fading to a pale purple. And this is because the energetic particles interact with the hydrogen in Saturn's atmosphere and create this particular glow. Here are views taken on Saturn's night side of Cassini's last resting spot at 9.4 degrees north and 53 degrees west. The spacecraft was coming in at over 35 kilometers per second for that final plunge. On the left, you can see the visual and infrared mapping spectrometer image taken at 5 microns. You're seeing the heat coming from the inside of Saturn, and the dark regions are the clouds that are higher up that are blocking that internal radiation. And that white oval is the location of the final plunge. And as I said, we took these final images on the dark side of the planet, and so you see on your right, that's a visible image, but it's taken in ring shine. So the dark side of Saturn is being illuminated by light coming from the rings. We have many interesting new results. You'll hear a status report of a few of those here today, in particular about the interior of the planet. The gravity team has been hard at work looking at the data, trying to understand Saturn's internal gravity field. And it's not what we expected. It's very different from what the models would predict, especially in the even harmonics. And in fact, Saturn gravity field and the Jupiter gravity field are very different. And so as the calibration proceeds, we're trying to get more precise orbits and the orbital timing for each of the gravity orbits, and we'll have more information about Saturn. Once we resolve Saturn's gravity field, we'll have a better handle then also on the mass of the rings. And to talk about the magnetic field, pass it on to Michele.
Okay, hello everyone. For the magnetometer team, the end of mission orbits were exactly what we needed to be able to get an understanding of the internal planetary field which is generated inside of Saturn. Based on the observations we made prior to the end of mission phase, the real surprise is turning out to be the fact that the tilt between the rotation axis of the planet and the dipole axis is really small. We had set a limit of it being smaller than 0.6 degrees. And this is a surprise because our understanding of how magnetic fields are generated is that it's done via the planetary dynamo process in the interior. And our understanding of how planetary dynamos work suggests that you actually need for there to be a tilt between the dipole and the rotation axis. And so essentially, by getting inside of the rings, we were just above the cloud tops, we were away from the currents being generated by the rings, currents being generated in the environment around Saturn. It will allow us, or it is allowing us rather, to really focus on the signal coming from the interior. And we need to be able to resolve this tilt between the dipole and the rotation axis to be able to work out the rotation rate of the interior of Saturn, and thereby to also work out how long a day on Saturn is. We know it's around about 10.8 hours, but based on the observations we've made so far, we can't be more certain than that. Now, the fact that we haven't been able to measure this tilt yet, all we know is that it's really very small, points to the fact that there's probably much more sophisticated dynamics taking place inside of Saturn than we thought. And perhaps it's something like this. Now, this is a rather complicated image. This shows you a view from some modeling work which was done of potentially what the dynamo region looks like. And so what we have on the outside is we have these field lines coming out of the interior of the planet. The blue are pointing radially inwards, and the red field lines down below here are pointing radially outwards. And you've got these very complicated processes taking place inside. You've got toroidal and poloidal fields being generated by the complex dynamo processes taking place in the interior. But by being able to measure the magnetic field lines outside, they allow us to start getting an understanding of what's actually going on inside. It's almost as if you can use the magnetic field to see inside Saturn itself. We think there's a solid core, then there's a dynamo region where currents flow, and those currents are what generate the magnetic field, and then there's the region above that. And we think that the region where the dynamo is being generated is a region of metallic hydrogen where the electrons have been stripped off the hydrogen, making it electrically conducting, and that allows currents to flow, which then generates the field. And longer term, what we plan to do is we'll combine the magnetometer results with those from the gravity observations, which Linda mentioned, because by being able to do that, it will allow us to get a much better understanding of the internal structure, potentially the size of the core and the size of the dynamo region too. And so we're working the data extremely hard at the moment. We've still got a lot of calibration work that we need to do, but we're beginning to get closer to understanding the internal field. We've now placed an even tighter constraint on the tilt. We think it's less than 0.06 degrees, so every time we place a constraint, it's getting smaller, but we hope to have an answer within the next few months. So I'm now going to hand over to Mark Perry, who's going to talk about the IMMS observations.
Thank you. Right, thanks. Okay, let's see. So I'm going to talk about the mass spectrometer. It's a tale of adventure and discovery, and started about 40 years ago when Voyager 1 passed Saturn. This is a plot that shows some of the results from that. It shows the density of the electrons and ions, higher densities on the right, lower on the left, versus altitude, higher on the top, low on the bottom. The dashed line shows the predicted densities of the electrons and ions in Saturn's upper atmosphere, and they're about 10 to 20 times more than the measurements, which are shown in the solid line. So looking at the measurements, sorting, once those are verified, it turns out that there was something missing from the model, and that was the effect of a small amount of impurities in Saturn's hydrogen atmosphere. And those impurities could be less than 0.01%, but what they would do is they would act as a catalyst and remove some of the electrons and ions from the atmosphere. So the Voyager observations were remote observations. They didn't have the sensitivity to identify what this, or even see this impurity. And even Cassini, with its much improved instrumentation, with remote observations, could not find this impurity. We actually had to fly into this area through the atmosphere and measure these molecules directly, which the mass spectrometer can do. It measures individual molecules and their masses. So Jack Connerty and Hunter Waite back in the early 80s did some great deductive work to figure out that these impurities were the cause, and then so that the trick is now to identify. Well, with the rings being more than 90% water, you'd expect that they predicted, and everybody agreed, that water is the most likely species. So this is what we wanted to do with the mass spectrometer. This colored line shows the track of Cassini as it threads its way between the rings and Saturn. Saturn's atmosphere, this hydrogen, actually extends almost up to the rings. It's very tenuous up there, but it fills this space. And the red shows where the densities are highest, and this is where Cassini is closest to the Saturn's surface, and this is where we would hope to find the water. So what did we expect to see? We expected to see hydrogen, and then we hoped that we would see water as well. Okay, so maybe this plots something only a spectroscopist could love, but it's really exciting, and I want to explain it. So we did expect to see hydrogen. That's 99% of the atmosphere, and we did. And actually, the amount. Oh, and I should also say, what this plot shows is every mass that INMS measures. Lower masses on the right, higher masses, lower masses on the left, higher masses on the right, and hydrogen. At mass 2 is way off on the left. And the amount we find is pretty much what was expected. The next thing we wanted to find, though, was the water. Well, water's mass 18, it's not there, okay? Well, before we got too upset about that, we noticed that right next to it is a strong signal for methane. And a couple things about methane. First, it could act just like water as the impurity in the atmosphere that removes or decreases the amount of ions and neutrals. So that way is fine. The problem is that it shouldn't be there. What we're seeing is things that come from the rings, and methane is volatile. It's highly volatile. It shouldn't, even if it's in the rings, it shouldn't last very long, and it shouldn't. And none of the models, none of the analyses predicted methane at all, let alone in this abundance. But there was other stuff. This is mass 28. Could be nitrogen, could be carbon monoxide, could be C2H4. Again, none of the models predict this. We were kind of working on some analysis that said there might be some carbon monoxide that comes from the rings, but nothing in this magnitude, and certainly not this much more than the water. But the biggest thing that we found was at the really high masses. So these signals are at the noise level. So when we first this was the highest pass that Cassini took, right up next to the rings. And we see this, and these signals are kind of in the noise, and we're trying to figure out if they're real or not. Well, the good news is that Cassini went lower in the atmosphere, actually in 2 different steps. And we find this, and we found out that these things are real. But this provides an even bigger problem, because there certainly shouldn't be anything this massive in the atmosphere, or certainly coming from the rings. As a scientist, there's the only thing more exciting than finding results that completely surprise you is finding the answer to them and learning how to explain them. We don't have that yet, but we hope to soon, hopefully within a few months. So, thank you. Oh, and Matt's going to tell you about the rings, I think.
All right, thank you. I'm going to start out by showing you this movie. This is just it's just a lot of fun. So imagine yourself sitting on board the Cassini spacecraft as it descends down through the ring plane, and you're looking outward, and you're seeing the rings from the inside out. It actually collapses down to a line and then starts to open up again as you go further down and start looking up at the underside. Here's an alternative view of the same kind of thing. So here you are embedded down, you're standing between the rings and the planet, and to your left, looming up is the planet Saturn, and the bands over here are the shadow of the rings being cast on the planet. And then this is the upper extent of the atmosphere, and then extending outward in the distance are the rings. You are inside the rings looking out upon them. So from this vantage point, and just as much, not only from the grand finale orbits, but just as much from the ring grazing orbits when we were perched just off the outer edge of the rings, these are, for the first time in the mission, ring flybys. Like the satellite people have been doing this all through the mission, and we ring people had to figure out how to do this, and we had to do it once a week. We're flying really close to the rings and getting amazing images. I'm sorry, and this is an extended version of that mosaic. Here's another mosaic that was taken as Cassini was descending between the rings and the planet and looking out upon the rings. So as we were getting these ring flybys, there were a number of things that we took very close looks at. The first thing I'm going to talk about is propellers. So this is a simulation of what happens in the ring. So each green dot is a ring particle. There's some million or two of them in this simulation. And the kind of the red and yellow is a moon that is embedded in the disk. And these are important because this is a window onto planetary formation processes. What happens when baby solar systems are forming is that you start to get the seed of a planet, but it's embedded in a disk. And so the disk is affecting the embedded mass, but the embedded mass is also affecting the disk. And we want to know more about what happens in both directions, and propellers give us a window onto that. This is back in 2004. We got some fleeting glimpses of propellers, and they were smudgy, they were tiny. We thought we'd never see them again. These are swarming in the middle part of the A-ring. This is the region we call the propeller belts. We ended up then seeing them a bit of a larger class, still swarming in the propeller belts. These are a larger class than the ones that were seen at the very beginning of the mission. Here's to the same scale the ones that were seen at the beginning of the mission. So what we saw with the ring grazing orbits were views like this. So it's just a spectacular increase in detail. We see this green square is the same size as that original image from 2004. And so you can see that we're seeing that same class of propeller, but in much more detail than we saw them before. But we are also seeing the class of propeller that we saw through the rest of the mission swarming in the propeller belts. And here, for the first time, we see the small ones and the big ones in the same picture at the same time, and we see lots of them. So we're going to be able to count them. We're going to be able to do a detailed study of the size and how they're distributed. It's very exciting. We're just at the beginning of this, but this is also just a spectacular image, very beautiful. This is a density wave from a much larger moon that's outside the rings, rippling through that the propellers are swarming around. So the propellers that are swarming that I was just talking about is one class. Those moons are about 100 meters across. There's a second class of propellers that are about 1 kilometer across. These ones are much larger and rarer, which makes them easier to track. Because they're larger, we can see them from farther away. And because they're rarer, when we look back at the same location months or even years later, we can be confident we're looking at the same object. So this then turns out to be the first time in the history of astronomy, to my knowledge, that we are tracking the orbits of an object over years of time that's embedded in a disk and not orbiting in free space. And we see the orbits are changing. This is a propeller that's nicknamed Blériot, is the one that we have seen the most often. It's the largest of them. And so you can see here, this is going around Saturn once every 18 hours for 10 years, and the margin here is plus or minus a degree of longitude. So this is a well-behaved orbit overall, but on top of that we see these excursions going back and forth. This is the disk acting on the moon at the center of the propeller, similar in some respects to how a protoplanetary disk must be acting on a baby planet as it is forming. And so why is it happening? Is it because the Blériot moon is colliding with individual ring particles? Is it because it's reacting with the overall gravity of the disk? Or I think it's a combination of the two. So I'm going to give more details of that as needed. We looked in one last time at these propellers on the last day of the mission. You can see here at the center of this image is Blériot. This one here is Earhart. This one here is Santos Dumont. These particular images are not particularly special, except they're one last data point in that slide that I showed you before for a campaign of a couple of years of trying to get what these orbits are shaping up to be. We also did close-up flyby images, targeted flybys of Santos Dumont, which is shown here, Earhart, which is shown here, and Blériot, which is shown here. I probably don't have time to get into details, but I'm glad to do that as needed. And now Linda's going to come back up here and talk about one last rings result.
Well, with all of these Cassini orbits getting so close to the rings, getting close-up views of the moons, getting their masses and orbits, has allowed us to answer some questions about what confines the rings of Saturn. You can see here from outward in, the C ring is very faint, the bright B ring, Cassini division, and then the A ring. And we know that the B ring edge, the outer edge, is held in place by a resonance with Mimas. So it's keeping the B ring from spreading. But the question is, what was keeping the outer edge of the A ring from spreading? Initially, we thought it was a resonance with the moon Janus, 7 to 6 resonance, but now that we had the masses and the orbits of the moons, it looked like it really took a group of 7 moons working together to confine the outer edge of the A ring. And if these moons weren't working together, the A ring edge would have spread out over hundreds of millions of years, and the A ring would be gone. So those moons, that team that contributes to confining the rings, include Pan, Atlas, Prometheus, Pandora, Janus, Epimetheus, and Mimas itself. And what each of these moons do is they create density waves. Their gravity creates these waves in the rings, and in creating the waves, removes angular momentum from the rings, so it slows the spreading of the rings. You can think of it as a stream flowing downhill, and if you have large pebbles in the stream that will impede the flow of the water, slow it down, and in the same way, all of these density waves are impeding the flow of momentum outward in the A ring, such that at the outer edge, the Janus 7 to 6 resonance can hold the A ring outer edge in place. And this is research that's done by Radwin Tajin, and he'll be has a paper coming out about it. And also, in looking at future talks, there's a plenary session right after this. You'll hear a little bit more information about the grand finale. I'm going to show a short video. Mark Perry's talk is tomorrow afternoon, and Rodwin's poster is Tuesday afternoon in the poster hall. And over the course of this week, there are many other talks and posters about the Cassini mission and the grand finale results. Thank you very much. We're happy to take questions.
We'll take questions. Rick will pass the mic, so wait for the mic and announce your name and affiliation before you ask the question.
Yeah, this is Alex Witzy with Nature. My question's for Mark. This methane and other unknown stuff that you see, how do you know it's infalling from the rings and not from somewhere else, like the planet itself?
Yeah, part of it, there's a couple. We've been able to calculate the distribution by looking at the signals from 3 different levels. We have right up high inside the rings, a mid-level one, and then right at the lowest level. And seeing how that distribution changes, for example, the concentration is highest at the highest altitudes, and it drops low, which means these materials are entering from the upper atmosphere. We also see that the concentration at the highest level is concentrated right at the ring plane. So these materials are entering plus or minus 1 degree from the equatorial plane. And so not only do we know they're coming from the top, but they're coming from the rings. Yeah. It was really cool to find.
Unexpected.
We got really, I didn't say this, but we really hit the jackpot with this, with the mass spectrometer results, which is much more than we expected. Yeah.
Rick?
Yeah, this is Rick Feinberg, AAS press officer. I'd just like to follow up. How do you explain, or how are you thinking of explaining the apparent lack of water that you were so much expecting to see?
So it turns out, so to answer that a little bit involves some particulars of the instrument. And water turns out to be a little bit hard for INMS to measure. It sticks to the walls of the instrument in this particular mode. It turns out that the water was there. We've been able to, again, verify this with the lower things and do a little bit more careful analysis. I showed that spectrum was pretty much a raw one. It didn't show a lot of the details that we've learned since then. But its abundance is roughly the same as the methane. So we think the water is there. What we can't explain is why isn't it much more than anything else. That's the confusing part.
All right, any other questions?
I'll just keep following up on that. So what abundances, and I can actually, I'll ask Linda a question too. What were those abundances then for?
We think, so there's a problem there. We think it looks like the abundance is fairly close to what was predicted 35 years ago by Jack Canardi and Hunter Wade, about a mixing ratio of about 10 to the minus 4. The problem is that it appears that water has that mixing ratio, methane has that mixing ratio, mass 28 has that mixing ratio, so there's something going on we don't understand. Another peculiarity with this instrument is these, so anyway. So we don't really know yet. Those are, again, those are raw numbers, and the way when molecules, the way INMS measures these molecules is the first thing that happens is they ram into the interior, the inlet system. And during that process, there's a lot of fragmentation, and we're really not sure how that's affected our results.
Right, these are higher speeds, I think, than anything INMS has ever seen before.
It was
That'll
not-
be part of the puzzle, probably.
Yeah, INMS was designed for the 7 kilometers per second. It saw a Titan, and here it's 30 kilometers a second. These molecules hit the instrument carrying an enormous amount of energy, and there's fragmentation, and we haven't sorted out that. So it may be concentrations are much lower, and we're just seeing fragments of molecules.
Kelly?
Sorry. Kelly Beatty, Sky and Telescope for Matt. These images that you got toward the end, showing the rings splayed out like that, have you discovered that there's a limit to the spatial size of the individual ringlets? Does it keep going down to the limit of resolution, or is there a smallest size for a ring?
We have not found a smallest size of the ring. There are certain images that I didn't show that have ring structure. It looks like it's azimuth flow goes all the way around at the pixel scale. There are other instruments that are actually able to probe that to finer scales than imaging is, the occultation instruments namely. But imaging has an advantage over those because imaging can tell the difference between a local disturbance and an actual ring, kind of a ring feature. But yeah, we were going down to a few hundred meters per pixel, and we did not have, we were seeing things at that scale.
What's incredible is as we got closer, places, especially in the B ring, just seemed to resolve into more and more and more individual structures, and just was very beautiful.
Any online questions? Or?
Well, let's see. There was one, but it was about methane, and I think we beat that one to death. I actually have a question. Again, this is Rick Feinberg, AAS press officer, probably for Linda. Not sure, though. You talked about gravity and how the gravity field of the planet is more complex than you were anticipating, and I'm wondering if you think that's going to have any effect one way or another on your ability to estimate the mass of the rings, which I know is one of the things that you're especially eager to do.
Right. The ring mass, we do have a signal from the mass of the rings. The problem is the error bars are quite large, and until we resolve some of these ambiguities about the model for the Saturn gravity itself, we won't have a number for the mass of the rings. But to first order, it looks like it might be a little bit less than we expected. But like I say, the error bars are so large, it's hard to say anything definitive yet.
Kelly?
This one's for Michele. One of the interesting results from the Juno mission is the confirmation of some theoretical work that Jupiter basically has a fuzzy core. It's not a real, just a bowling ball in the middle. Do you have any expectation that we'll find that at Saturn? Do you see anything yet in the data that has you thinking in that direction?
We still need to work the data a little bit more. We're hoping by the time we are able to incorporate data from all of the orbits that we will start getting an idea about the core. But at this stage, we've only calibrated we're only comfortable with the calibration of the first 9 orbits. So ask me that question again in a couple of months.
So do I take from that you think in the data, once you have the full data set, there will be something of an answer?
Yes.
So while we're on the issue of comparing giant planets, I wonder if I could ask Linda to expand a bit more on gravity fields between Jupiter and Saturn. You said they look like they're different. Can you expand on that? How are they different? What is different about them?
I can expand a little bit, but some of the information for Cassini is embargoed. But for Jupiter, to first order, the even order harmonics followed the model as expected. There are some differences there, but it really did a pretty good job following the models. In the case of Saturn, there's a difference as you go to the higher order even harmonics, and so it's trying to explain the source of those differences. And so that's the key, without giving any numbers for it. The gravity team is hard at work on this, hoping over the next few months. Part of what we have to do is get the orbits pinned down more precisely. As we got in closer to Saturn, we experienced some drag from the atmosphere, et cetera, and just to pin that information down, get great as-flown orbits. That's the first step, I think, for Michele as well.
Yes, that's right. We need to get some of the spacecraft trajectory back to much higher accuracy than we've got it at the moment. And once we've got that, then we can start pinning down.
And at the speeds we're flying and how close we are, it's important to really do a good job on the trajectory.
It's like ping pong. So for Michele, could you no, I'm sorry, Mark.
All these M's, huh?
Yeah, I know.
The trajectory doesn't matter to...
No, actually, I think it is, Michele. All right.
I'll also pass it on if it's not.
The co-alignment, the very close alignment of the dipole with the spin axis. You said that dynamo theory requires an offset in order to generate the dynamo. Can you walk us through why that is and what is your plan B?
Plan B. Okay.
If you're co-aligned and
Yes.
you need an offset, then what's generating the field?
Or is it dying? Yeah.
Well, that was one of the thoughts, that the field might be dying, but we've been able to measure higher order moments, so that's not an answer. It will change our understanding of the way in which magnetic fields are generated. Still via planetary dynamos, of course, but it will be, our understanding to date, based on other planets, Jupiter and the Earth, for example, is there is a substantial tilt between the dipole and the rotation axis. And a first-order understanding of planetary dynamos is you need that non-axis symmetry to be able to continue to generate the field. Without it, you don't expect the field to be able to be generated. And so the implication...
Because the convection is...
The currents, right?
Yeah, because of the currents. We've got an expert in the room, Hao Chow, who's on my team, who I'm sure will be able to answer this in a bit more detail if you would like it. But my understanding is that we're going to change our mind about planetary dynamos. But if you're happy to ask Hao to answer the question, then I'm sure he'd be more than happy to do so.
Okay.
Hao, are you happy to? Go for it.
Oh, okay.
Here's good. Okay, yeah. So about the question of the tilt between the rotation axis and the dipole axis, we do need it, at least in the dynamo region, for the dynamo to keep working. Why? Because if it's not there, the field will simply be decaying. It's very easy to prove that mathematically. If the field is perfectly axisymmetric with respect to the spin axis, you can show that the field will just keep decaying. And the decay time scale is very short, like 100 million years or so. So couldn't survive 4.5 billion years. So I think that was an answer on that.
Thank you, Hal. So much better than I could have done it.
I just wanted to follow up. You said there had been some supposition that maybe the field was dying because of this axis symmetry, but you saw higher order, you still see higher order moments. How do those couple together? Would you expect it to collapse first to a dipole, simple dipole, or what?
That's right. If the field was dying, then you would expect the higher order moments to decay much more rapidly than the lower order ones. And so the fact that the work that Hal's been doing is we've been able to take the internal planetary field model up to degree 9 so far. It's purely axisymmetric still, but the fact that we can measure those higher order moments is implying that those higher order moments aren't dying, they aren't decaying away. So that's not the answer.
Could something be masking the field?
Yes, there was a theory put together by Dave Stevenson back in the 1980s that there is a region above the dynamo region which is essentially electromagnetically filtering out the signal coming from the interior. So you have a non-axisymmetric field being generated in the dynamo region, but something above it is filtering the non-axisymmetry out, and so you're able to only measure a purely axially symmetric field. That is a thought as to what. That's one of the ideas that's been put forward as to why we're seeing this axisymmetric field. We would hope to answer it in a few months. Every time someone says to me, "How soon are you going to answer it?" I say, a few months.
It's there.
I never give an exact date.
All right. With that, we'll end this press conference. I encourage everyone to go to the Cassini talks and posters. Also, we'll be back tomorrow at 12:15. For tomorrow's session, we'll have 3 more interesting talks. Also, there's a JPL press release just now, a few minutes ago, on this press conference. So see you guys tomorrow.